Okay, let's get started. So, sapere aude. Somebody wants to motivate us to think on this blackboard. That wasn't me. So, where did we stop last time? Diffusion maps. And we didn't quite finish with this, so I want to finish that and take a step back, give you an overview of all these different dimension reduction methods that came out of the last 30 years of machine learning research, but only very rough overview because there were so many different ideas. Most of them never really worked as greatly as people had hoped. But we'll see a bit the evolution of these ideas, and then we might dive in a bit more. I don't know how far I got, so I prepared something which probably keeps us busy now and next week. Before I forget, there's nothing this Wednesday, because on Wednesday I'm supposed to entertain the systems biology master students, and that will be a whole day block course. Okay, where did we stop? We looked at this diffusion on graphs, and I think I will quickly open this again while we go through this again. And let me, I have so many things open here. I better restart everything here. Restart R and run all chunks. Okay, while this here runs through, let's have a quick look at what we did last time. We talked about this idea of diffusion on graphs, where we used the diffusion process, and that originally stemmed from this treatment of heat transport by Joseph Fourier, and was starting point of the Fourier analysis, and that we now also use. And maybe you haven't noticed it, but we have looked at through different ways of modeling such a diffusion process on a graph. And I haven't really explained what the difference between the two is, and it's actually also not quite so clear what the difference is. It's just two different ways of generalizing the same idea. One idea, the first idea we looked at is that we said we'll try to put the heat equation. So you remember this thing, U dot is nabla squared U, and try to move that in a discrete finite difference manner onto the graph. And we said to do that, we have to say that we sit on a vertex and we assume this vertex has a certain temperature, and then we move, and when we say that the rate of change of this temperature, so the derivative with respect to time of the temperature, should be proportional to the temperature difference to the neighboring graph. So we said we have to add up the differences to all the neighbors, and then we realized that this gives us something like the graph Laplacian, which is written d minus a, where we can say the element ij on this thing is delta ij minus aij, delta ij times di minus aij. Di is the degree of vertex ai. Aij tells us whether these two vertices are connected or not. And we came to this by saying, well, if we go over all the neighbors of a graph I, then this is not equal, but we said we change in the temperature on the graph on the point ui. So temporal derivative should be something like the sum over all the neighbors of I, and we say what is the temperature at the neighbor minus the temperature here. And it's proportional to that. And then we said, therefore, we have here this, we get here this thing, the first part gives us the sum over the neighbors, that's that part, and the second part gives us the degree because for each neighborhood we sum up this thing once, and that's how we got to the graph Laplacian. So that's what we started with, and then we said we now want to solve this differential equation here. And to solve this differential equation, we diagonized this Laplacian so that we can then write solutions which show us how a certain heat pattern diffuses by putting some initial condition where each graph vertex has a certain initial point, initial temperature, and when we see how this evolves. And we notice that this graph has eigenvalues, where each component of a value is the temperature of one node, and each of these eigenvectors decays with a specific decay constant, and that allowed us to make up any arbitrary initial condition as a sum of such eigenvectors, and each eigenvector then decays with a constant, and this allows us to see the temporal evolution of this heat transport. And the reason why we did that, how we applied it to our single cell case, is that we said instead of transporting heat, we just transport some abstract probability, because we want to know in our big feature space, if we are sitting on one cell, how do we get to another cell in order to see how similar two cells are connected. And now imagine in our big feature space, we have cells which sort of are spread out over some banana-shaped space, maybe sitting on this curved manifold and spreading around it. And we always want to understand, and just to remind us of what our overall goal was, we have our single cell data, which allows us to put the cells into the state space, and when we want to know which cells are similar and what kind of evolution can we see. So that, for example, if it looks like this, that we can see this type of cell can either evolve to these cells or to that cells. And we recognize in evolution as being possible by saying there's sort of a path to get from here to here by going over lots of intermediate states. And the fact that these intermediate states are actually possible and exist in biology, we infer from the fact that we see cells in this state. And this is why our fundamental question is always, what kind of state transitions can we interpolate by going from a starting state to a final state by going over all the intermediate states that we actually see in our data. And this, of course, means if we want to ask how far it is from this state to that state, we shouldn't measure directly along a Euclidean distance, but we should measure along this manifold. Let me, just in case somebody should ever watch this, if I do it like that, then we can see the board. So, and hence, this is why we try to find some way of finding sort of curved trajectories which go from here to here and go through the different things. And we looked at now these two aspects of doing this. Either we said we use this principal curve idea where we just try to find a curve which always stays close to the points by finding a curve which minimizes the projection distance of the cells. That was our first thing, which we can call sort of the analytical way, because we just used this spline regression here. And the other way would be this graph way, where we just connect each vertex, which is nearest neighbor, and completely forget about directions and about our original data. All that we retain is the information of which cells are in each other's neighborhood and what's the distance between them. And then we try to find a process which hops from here to here. And in order to see this process, one possibility to do this is to use this heat transport process as an inspiration by saying we start with a piece of heat here and ask when does this energy have added up at the other part, and use this differential equation system that we've done there. And we can do this in two manners. We can use this continuous aspect that I showed you first, where I said we want to simulate a continuous function each vertex has a certain temperature, and we want to have a continuous function which tells us how this temperature changes with time. And hence, we have noticed that there is certain eigenstates which don't change their pattern, they just change their amplitude, they exponentially decay, and in that way we can start with an individual thing like putting one big point here, making this point hot, and asking when does that point become hotter, and we can solve this by going through this eigensystem. The other thing that we've looked at was to go through, to mimic the diffusion process not as a continuous time evolution, but it is a discrete process where we always say there's a unit of energy here on this vertex, and at each time step, this unit steps to a randomly chosen neighbor. And this is called a random walk on a graph, and it's typically, and it's considered as sort of one of the prototypical examples of a Markov process, where we start at one point, and then we have our state is now again a vector with one element per with one component for each cell. But before we interpreted this vector as some kind of temperature, which diffuses around, now we interpret this as probabilities. At the beginning, we say the walker is at some point, so it's probability 100% there and 0 everywhere else. And when we switch, and when we let this walker jump and always choose, and after one step, it's with probability 1 over d at each of the d neighbors, and in that way, it spreads out the probability. In a way, the two things are not so similar, because if we consider the heat as the temperature as energy, then of course there's energy conservation, and the sum of a heat energy over all the vertex elements should stay constant over time, and the same is true here for the probability, which should always add up to a fixed 100%. So in that case, the two aspects are not quite, are rather similar. Only in one case we have a continuous evolution, and the other we have a discrete evolution. The odd thing is that the math looks a bit different. In the continuous evolution, we had here this process where we said the time derivative d of dt of this vector u should be some constant times the Laplacian of u. This would be the continuous process. So the heat diffusion. And then we have the discrete process, a random walk. So let's stand here with L is E minus A. A is the adjacency matrix. And E is the degree matrix, which is just the row sums of this adjacency matrix. So in the diagonal, it only has entries in the diagonal, and all the diagonal elements are the number of vertices in the thing. In all these cases, so far I've always said A is binary. It's either 0 if they're not neighbors, and 1 they are neighbors. But people also like to make this a little bit more smooth by saying they put a kernel over it and they use the neighborhood distance and saying something like Aij might be, for example, e to the distance dij over some kernel square. So that a near neighbor has a larger edge weight than a far away neighbor, and you hope that this sort of smoothly goes down to 0. I will show you a lot of different ways how to do that, and the next time we can discuss a bit about how we get to different results depending on whether we are discrete or continuous, and whether it really makes a difference, or actually why it turns out to not make much difference, whether we use something continuous or whether we just binarize this matrix and say we don't care about the distance, we just say it's either 1 or 0. But for now, let's see again what we had. We make our discrete random walk, and in our random walk, we said u at the time t plus 1 is given as u at the time t, and we apply some transition matrix, and that transition matrix, that was A times D minus 1. So the way how this now works is that we said if we want to go in with 100% probability on one vertex, and when we go through the adjacency matrix, then of course afterwards we have 100% on each neighbor. And in order to make sure that it's afterwards still normalized, we have to multiply before each component, we have to divide each component of the incoming vector by the degree, so that after it goes through the adjacency matrix, it adds up again to the proper total. So as you can see, we have the two things look a bit different. Here we have something called D minus A, while here we have something which is multiplied. So the way how our adjacency matrix and the degree diagonal matrix get combined is a bit different between the continuous process and the discrete process, even though both have a purpose of making sure that the U stays normalized. Of course, what I should say here I have the time derivative of U. So to make this comparable, maybe what I should write down here is something like the change, so ut plus 1 minus ut, and that is, of course, now t minus I times ut, and then I can again write this as ad minus 1 minus the identity matrix ut, and now we will later see that you can do some strange kind of renormalization by saying let's multiply this whole thing here from the right by d, and then again we have a minus d. So in that case, these two things are not that similar. If you look at this here and at this here, if you just put the normalization on the other side, then you can push the d on the other end. So now how did this look in practice? Let's look back at our code, because we did both. We first tried the continuous process, and then we tried the discrete process. And the continuous process, unfortunately, I haven't really cleaned up my R file yet. So I show you here the discrete process. And this runs under the term diffusion distance. So whenever in the continuous process, this runs under the term Laplacian eigenmaps, and the discrete case under diffusion distances. And as far as I've noticed, the literature sort of discusses these as completely separate points. It seems that most of the machine learning community prefers this continuous case, the Laplacian eigenmaps, while in the single cell field, everybody works with these discrete case diffusion distances. So it dawned on me that maybe it's worth comparing the two and see what we get differently. So let's have a look at this. So this is what we did last time. I used our usual single cell RNA-seq data, again with adult neurogenesis data, where we start here with stem cells, which then cycle and become neuroblasts. And we made an adjacency matrix from this by connecting each cell with its, say, where are we here? 15 nearest neighbors. And here you see I make this list of vertex A connected with its neighbor. I make this once for the first, second, third till 15th nearest neighbor, and then I construct my adjacency matrix. And then we do this discrete case for random walk, where we first said, let's normalize the adjacency matrix, that if we come in with 100% probability on one weight, we go out with 100% probability. And for this, we have to divide everything by the rows. And then So this is with times d minus d to the minus 1 that we have here. And here you see this UMAP plot where we start with 100% probability on this blue thing, and then we go through it one, and then of course each of these 15 neighbors, here shown in magenta, has now probability 1/15. And we can go through this another 10 times by always multiplying the vector again with the transition matrix. And then we get here, after 15 iterations, we get this probability distribution. Just to make things a bit more annoying from notation, take care in the continuous process, people always put the state vector u to the right of a matrix and multiply in this way to get the new state vector. And I've also written it here on my blackboard, but if you look in the literature, the Markov people, they always like to do everything in the transposed picture. So they say my state vector is a row vector, which I multiply from the left with a transition matrix to get the outcoming matrix. So I've put this here like this here in the code where I come from the left. And this is also why here I divided by the row sums, which would be multiplying d from the calculating d minus 1 times a and not a times d minus 1. But in any case, no matter which way around you write your matrices, you get after 10 things this. And then we were wondering, what do we do if we multiply this, if we want to do this not 10 times, but 1,000 times? Obviously, this costs us too much time to calculate this for each cell 1,000 times, so we went through an eigen expansion. We took this matrix, here you see now with d to the minus 1 on the left side, and said, I want to exponentiate this to calculate the diffusion after L steps of a random walk. You might remember this from last time. We expanded this in that manner, then said here this part in the middle is a symmetric matrix which we can diagonalize when we have here the eigenvectors and the eigenvalues of this diagonal, of this symmetric matrix, and when we get this thing. And now this is more or less where we stopped. We said we call this part here XL, which is, remember I come in from the left with my matrix, so I first multiply by this and then by this and this, and I call this XL and then stems here the right. The reason why I make my break exactly here between the lambda to the L and the UT is that this allows me, it's because this allows me to reduce my matrix to something much smaller. The transition matrix, if I have 10,000 cells, when this is a giant matrix of 10,000 by 10,000 elements, as long as I only have make a few transition, of course everything stays in the neighborhood and the matrix is very sparse. But for high exponents, this matrix T to the L quickly blows up and loses its sparseness and has values everywhere and becomes very big and unwieldy. But if we only calculate the matrix multiplication from the left up to the lambda to the L, the following happens. With lambda, these are the eigenvalues, and they are sorted in reduce. We are going down slowly in magnitude. So let's quickly see if this one has calculated. I'll find the point where I have just been explaining here in my code. Not yet. Here is where we stopped. Exactly. Here I take my, here I have calculated these eigenvalues. And if we look at these eigenvalues of this matrix, the lambda matrix, you see they start with 1. That's the biggest eigenvalue. It's associated with a constant state, so with a final state where all the heat has diffused over, where the walker is completely spread out over the graph. And then comes these other which are close to 1. But if I were to calculate, say, 300 steps, then you see these values go down quite quickly. And already the 10th or so eigenvalue is now below 100. And this is what we can use here. This allows us to look at this thing here and say, this matrix, all the bottom of these maybe 10,000 eigenvalues that we have in principle, one for each cell, only the top 20 or so will still give an appreciable contribution once we've exponentiated them to a big number, because they're all between 0 and 1. And hence, I can truncate all the right-hand columns of this matrix and say I only keep the left 20 or the left 50 columns, and the remaining 900 columns I simply omit because they will have hardly any influence on my result. And once I've done that, to get my proper result, of course, I have to multiply again with this ut and with d½ to complete my formula. But maybe I won't do that, and this will be our trick afterwards, that we just forget multiplying by that in order to stay in this convenient space where each cell is only simulated by this. So I show you how this looks like. Let's first check here that we make our exponentiation to 10 steps, and we want to get this one here out. And as you can see, what I've done is I calculate this matrix X, which is everything up to here. I call it XL, or now X10, because I've set L to 10. And I get here this matrix, and I only keep the first 100 columns. This is because here I used this eigensolver function to get me the first 100 eigenvectors for the 100 largest eigenvalues. And that's important because that can be done in a few seconds, but calculating all 18,000 eigenvalues would take hours. And hence, this thing now has this thing, 18,000 rows for the 18,000 cells, but only 100 columns. And as you can see, these columns, they go down in weight quite quickly, and the 100th column is much smaller in its total norm. So this is, in a way, it's the squared norm of the columns than the initial column. And that's why we hope that it's okay to omit the remaining 17,000 columns which come here to the right. So to see whether this really has worked, I now multiply the remaining part, which I was still missing, the transpose of the eigenvectors, and again this degree matrix, and get my new matrix U10. And I plot this vector, and this is now supposed to be the same as what we had up here. So this one here was calculated by simply taking the actual transition matrix and applying it 10 times to a vector which is initialized on this point. And that thing, now instead of carrying out the matrix multiplication 10 times, I've used the eigendecomposition and truncated to only the first 100 vectors. And as you can see, it works not quite perfect. Look at this part, for example, it's all yellow here. But in this one, there's a little bit of green smudge here. Also, a couple of values are a little bit below 0. So this is what happens from this approximation, that elements which should be exactly 0, because I would need more than 10 neighbor-to-neighbor hops to reach them, now scatter around 0. Here I've plotted for each point the probability to reach it after 10 hops, starting from my one cell, which I had green in the beginning. And this here is the exact calculation where the probability can never be below 0. And this is the approximation using only the top 100 eigenvectors. And as you can see, it's always a little bit wrong around 0.005 plus minus above or below it. But overall, it works good enough. And once I go now from 10 to maybe 100 steps, then of course, here I took, you see here with 10, the first 100 eigenvalues don't go down quickly enough. So I can't, that's the one I should make. Just a second, please, because I've made here a slight mess by reusing a variable name. So I have to recalculate my adjacency matrix. Here, ach verdammt, how far up do I now have to go here to get this again? N cells is Seurer sparse matrix. Should have put this in two different. So, transition matrix, we row sum these things. So here we see our first step. Now we do this 10 times manually, plot it when I do it through the eigen expansion, calculate here the top 100 eigenvalues, which you see takes a couple of seconds, but it's not dramatic. It should be finished any moment now. And now I can here see how this goes down with first 100 things if I calculate 10 steps. And if I were to calculate not 10 steps, but 100 steps or so, it goes down even more quickly. So and now we have this part here, and we compared the two results. And now I think this was about where I stopped last time, because what I can now do is that I calculate diffusion distances. The idea, this goes now back to a paper of two guys, Kreufmann and Lafon, who suggested this by now 20 years ago. And they said, in order to calculate the distance between two vertices I and j, we could in principle choose a number of steps and then say, let's evolve the probability distribution L steps starting from one of the points and L steps starting from the other of the points. And when we compare these two probability vectors by just looking at their Euclidean distance and say, this is our diffusion distance between these cells. And this diffusion distance has the property that it has an interesting length scale. Imagine this here, remember this is 10, this would be now 10 steps starting here. And imagine I would have another point and would say 10 steps starting here. Then this would diffuse up to here. And if I then ask, what is the diffusion distance between this and that, I would take the difference between that vector and the other vector down there. And that vector would probably be the maximum. It would be 1, because you can imagine that there is no overlap between this one and that one. So no matter whether I take the diffusion distance between here and here, or between the green one and that one, or the green one and that one, or green one and that one, it's all simply saturated distance. So our distance cannot grow anymore once the green things don't overlap anymore. So this diffusion distance with 10 steps can only sense distances which are sort of with a scale of about that wide, about the width that I now indicate with my mouse cursor. If the two initial points are further apart, the diffusion distance saturates and is always the same maximum value. And if they are much closer, if I were, for example, comparing this point with that point, the diffusion distance would be practically 0, because it has diffused so much that I can't really say whether the diffusion has started here or here. And on the first look, you might say, this is not good. Why would I want that the diffusion distance has this strange thing that it becomes insensitive to very small differences, and it becomes insensitive to very wide one. It has some kind of limited range where it can sense diffusions. But this can be quite helpful, because we want to smooth over small differences. Because whether a cell sits here or here is probably only an effect of Poisson noise. If I were to take the same cell, measure it twice, then sometimes I may get 5 reads from the genes, next time I get 7 reads from the same gene, and after the PCA, we might end up at slightly different places, but essentially they are the same. So we want a distance measure which smooths out over these small distances. And and by setting the step, we ask at which distance scale does it interrogate. So for example, we can choose a number of steps such that really it makes a huge difference whether we go straight or we go the detour around the cell cycle, or maybe if we take the steps large enough that the diffusion simply washes over this structure, this doesn't make a difference anymore. And that's something that is quite useful, that you can say, I want a diffusion distance which is sensitive to differences at this scale, or which are not sensitive to differences at that scale, but only at another scale. Of course, this means that in order to assess your stuff, you have to try different steps and then different numbers of steps and see which is most suitable to answer the question you want to answer at the moment. And I want to show you how this works in practice. And because if we want to try different steps, we have to find this in a manner which makes our life easy. So let's first skip our test steps and say, let's stick to what have I solved here with length scale. Let's stick to L equals, I think here I have used now L equals 10 for the beginning. So 10 steps. And as I said before, our first idea might be we start at a point at a cell I, evolve 10 steps, do the same at a cell J, and compare the two probability vectors. But that turns out to be not a good idea, because in order to do that, we have to calculate the effect here by calculating this formula here up to here. And now, once I've started with this 1 point and I calculate up to here, I now have a vector which describes the diffusion patterns, but not as a probability vector over all the cells, but only using the top 100 eigenvectors. So it's only a 100-dimensional vector instead of an 18,000 dimensionally. And then once I multiply it with this UT, the 100-dimensional vector gets blown up again to 18,000 dimensions. And that requires a lot of computation time, and the question is whether it's worth it. Because UT, after all, is a pure rotation matrix. It's an orthonormal matrix. So multiplying UT shouldn't change anything about these distances here. It shouldn't make a difference if I include the multiplication by UT or not, because if I rotate in the space, the distances don't change. However, what affects a change in the distance matrix is this times d to the 1/2, because it reweights our distances. So I can also, I can now decide, okay, but on the other hand, this d vector, you remember this is, let's look at this d vector, it contains the row sums of the adjacency matrix. And here I look at a histogram of that. And you see these row sums were always between, were always at least 10, because that's, we take the 15 nearest neighbors, so it's always at least 15, and sometimes it goes up to 40. Now in our formula, we multiply by the square, divide by the square root of this. And if we do this, you see it multiplies usually by a number between 4 and 6, sometimes up to 8, but rarely. So this last step here in the formula of multiplying here by d 1/2, which changes the individual components only by a factor of 2. So if you forget about this, some components will be weighted a bit too much and others will be weighted a bit too little, but it doesn't change so much, because the factor by which we are wrong is always about the same. Hence, we could decide to simply forget about this d to the 1/2 on the right-hand side and not multiply with that. If we don't multiply with that, we can also omit the multiplication by UT, because that's an orthonormal matrix, which doesn't change distance. So we stick and calculate our distances only in this XL. And that was this idea of Koifman and Lafon, that they said, here, instead of using this as the distance, we use this as the distance, where we only calculate up to XL, which is the same as calculating the full transition of L steps, but weighting the individual components according to the square root of the vertex degrees, which changes the Euclidean distance a little bit, but probably not too much. But now we can calculate this distance by just looking at the differences between these vectors, which, as you remember, only have 100 dimensions instead of 18,000, because we only need the top 100 eigenvectors, because those which are further down were nearly 0. And that now allows us to very quickly calculate the distance of a given cell I to all the other cells. This here should be a J, of course. And that's what I've done here. I've again stuck to this matrix here and calculated the diffusion distance with 10 steps to all the other cells. And as we've decided before, it doesn't make any difference whether we start here or here or here. The diffusion distance is always about the same because we hardly reach that. Only if, and in order to now see how the number of steps influences this thing, I can just calculate this, do this calculation that I've done with different step size. This is running 3 steps, running 10 steps, running 30 steps, 100 steps, 300 steps, and 1,000 steps. And as you can see, for each step size, there's an area where the distance changes quickly. This is sort of a length scale where this diffusion distance is sensitive. This diffusion distance understands changes on this scale, on that scale, on this larger scale, on that larger scale. And now we can go back and remind us what our original goal was. We wanted to understand the transition from these neural stem cells to these neuroblasts and onwards to the neurons. So we want a pseudotime that smoothly increases from here all the way to here. And obviously 30 steps seems to be not enough because it doesn't really allow us to see the difference between here and here. 1,000 steps is already too smooth. It makes everything the same pseudotime, and only those things which are really completely disconnected get different. But 300 steps, that might be just the right compromise, where we start here and go through here and over there. So I will now use this diffusion distance with 300 transition steps in order to define a diffusion distance along this thing. So how do we do this? I again calculate this matrix X here with 300. And we go back to the matrix. So this matrix XL here, which is just which we just make by multiplying this degree matrix, the eigenvector matrix, and the eigenvalue matrix taken to the 300th power. And this matrix is now a matrix with 100 columns, because we've chosen to keep 100 eigenvalues, and 1 row for each cell. And the individual rows describe 1 cell each. And if I want to calculate the distance of 1 cell to another cell, I just take the 2 rows from this XL and look at their Euclidean distance. So this XL matrix contains everything we need to know about our diffusion distance. And once we've calculated it, we can read off all the diffusion distances from it. And how can we now use this to do a pseudotime? What I will do here is I define a starting cell and a finishing cell by saying this here might be a good starting cell, because if I go here from this cell, you remember we've picked an arbitrary cell here and said let's start from this cell, and now we want to go from this cell as far as possible to the beginning of a lineage and also as far as possible to the end of a lineage. So I find some cell which is far away from my intermediate starting cell here within this cluster and within that cluster. This cluster here, that was the cluster number 0 here, and I plot all the distance values from my starting cell to the cells in this cluster 0. And here's a histogram of them. So as you can see, what I did is I calculate here this distance matrix, the distances of my arbitrarily chosen cell in the middle, that one here, which I just called cell, to all the other cells by taking the Euclidean distances between all the rows of my XL matrix. And here I plot these, only those which are in this cluster here. And as you can see, most of them sit here, they seem to peak here, and then there's a couple of 2 or 3 cells out here. And these are probably outliers. And maybe this is really the proper start, one of the cells which go down here. And we could say this might be a good cell to say here does the lineage start. And that's what I do. I just pick here randomly and say I want to have a cell which sits here at the orange line by 0.0013 in order to make sure that I don't pick one of those, and say this is my start cell. And I also try to find an end cell doing the same by plotting all these values here. And here is how these values look like. And you see where it probably makes sense to say this cell at the very end is the end cell. and I say this one, that is my end cell. And now I can calculate for every cell in the distance to the start cell and the distance to the end cell. And that's what I've done here. Each point is a cell. The green ones are the cells in the lineage. The red ones are the cycling cells, and the blue ones are all the other cells. So this thing here, that's the green one. From here to here to here up to here. These ones are red, and this stuff and that stuff I put in blue. Now you can see here how this works. This is the distance to the end, this is the distance to the start. So this cell here is the starting cell, this is the end cell, and these here are all the other cells now brought in a suitable order where they go away from the starting cell and get closer to the end cell. To see this a bit nicer, I rotate this plot now by 45 degrees and make the difference between start and end as my new x-axis. And this here, the sum, is my new y-axis. And now you can really see this is here the distance to the start minus the distance to the end. So this is the start cell, this is the end cell, and these are all the cells in between. And in fact, our diffusion distance brings all our cells now in a proper order. And that is now a very nice thing. This allows us that we've really managed by having our graph, which sort of spreads from here to here, and putting all the cells in a useful order, which tells us in which order we can, in which order the cells are reachable by diffusing through the graph. And here I've now plotted this in my UMAP by coloring each cell by this new pseudotime, which, remember, is the distance to the start cell, minus the distance to the end cell, and again the start cell is that one here, and the end cell is probably this one here, which is here. And as you can see, the pseudotime smoothly increases from here all the way to here, and then it increases quite rapidly along this last part where a lot happens over small distance. And these other ones, they of course also have a pseudotime, because all these blue ones here also have a pseudotime. They have an x-axis here, but that is of course not very useful. And hence, I should also plot here the y-axis, which tells us how useful this is, and only if this y-axis is below 0.01, we can say that this is useful here along this thing, and everything above 0.01 is probably nonsense. So that's why I plotted this here, making everything below 0.01 reddish and everything above 0.01 I made in blue. And now you can see, yes, our pseudotime works nicely along this reddish part from here to here. It's a bit questionable whether it works for the cycling cells. Maybe we can also use it for the OPCs, these oligodendrocyte precursor cells, but we definitely can't use them for all these other cells. But we don't want that. We wanted to use it for this lineage. And what you can also see here is how the cycling cells, they stick out here because sort of for a while we go away from both the start and the end cells, and then we come back. And that's why we see this sticking out. And that's a nice thing about this diffusion pseudotime, because whenever you have branching trajectories, imagine you have some stem cell which can either differentiate in this cell type or in that cell type. And now you pick a start cell here and an end cell here, and you make this plot to see whether, and you make this plot in order to check what's the distance to this start cell and what's the distance to this end cell, when of course what you will get is something like this, where this branch here is that part, this branch here is that part, and this extra branch is that part. And you can quite easily read off the branching part and hence tell each cell whether it's in this lineage or that lineage. And so this also helps you then to determine whether a cell goes to one branch or to another. Or you might take another end cell here and make a three-dimensional plot where you want to ask, when does a cell actually make a decision that it really wants to go here and not here? What is the decision point? How far away do I have to be from the start cell for the cell to be decided about its fate? That's something biologists are very interested in, these so-called fate decisions, where you want to understand how does a cell decide whether it becomes one cell type or another cell type when an embryo develops. And in order to be able to answer these questions, the first question we have to answer is, when does the cell decide that? And to do this, we can say here, this cell here has equal distance to that one and to that one, but once we are here, it's closer to this one than that one in the diffusion distance. And this allows us to pinpoint where the cell starts to really be closer to one thing and to the other, and where exactly this branching happens in our pseudotime. And this makes these approaches quite valuable. So now, last time, or last week, or was it 2 weeks ago, we used this principal curve algorithm, where instead of using this neighborhood graph, we didn't look at all at neighborhoods. Instead, we used this principal curve, where we said we will want to find a curve which goes as close as possible to all the points. And now I say, I want to compare, does this look similar or different? So I take all these, I take all the cells which are in the cluster, so all those here, and use this principal curve package again, which now finds a curve which goes through the middle of all these points, minimizing the squared distances of the points to the curve. And I do this and I get a principal curve. When I do the same that I did last time for all the others, like those on the lineage, I project them onto the curve, and now I get here this pseudotime. And here you see how the principal curve, it starts here, the pseudotime, and now the curve goes along here, 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 and the color always tells us if you project the cell onto the curve, how far from the start of the curve is the cell, is the projected point. And as before, we see that it smoothly increases from here to here, and then it jumps over here. And a lot happens here. And then I thought, now let's plot the two points. Now each cell has two pseudotimes, one from our diffusion process and one from our principal curve, and we can compare them. And that's what I put here. The green ones are the lineage cells, the red ones are the cycling cells, and blue ones are those which are actually outside the lineage. On the x-axis, the diffusion pseudotime, so which is calculated by looking at the difference between the diffusion distance to the start and to the finish. And on the y-axis, the principal curve, which pseudotime. And as you can see, it sort of agrees quite well. Here in the cell cycle, of course, there's some confusion about whether the curve goes this way or that way. But overall, it works reasonably well. And here it also works reasonably well, except for these cells here, which seem to be a bit unclear about that. So, there's now two rather different ways to find, deal with the fact that we imagine that our cells have some elongated, long elongated manifold, and we want to get some one-dimensional coordinate which increases along the long dimension of these manifolds, and which doesn't get confused if this thing isn't straight, but it's waving or circling through this manifold. And before I finish with that, I wanted to show you a few more aspects of this so-called diffusion space, this idea of Koifman and Lafon. Let me show you the paper, by the way. Maps. So here cited 3,600 times. And as you can, so this was this paper of when did they write that? 2006. And the thing that they then added in that they next did is they then also argued that this space XL, you remember this matrix where we don't do the back rotation from the diffusion space into our feature space, which has only 100 dimensions, that this is maybe useful. Let's look at our at the XM matrix that we've just calculated and that we used for our diffusion matrix. where is it? X 300 steps here. I have this distance d, which xm I called it. This is this matrix. This is this matrix, which has for each of our 18,000 cells a row with 100 dimensions. And these 100 dimensions, if we look at them, all sums, these squared sums, you can see that they go down quite quickly. In practice, only the first 10 or so dimensions actually have an appreciable weight. And once I'm above 10 dimensions, this eigenvalue to the 300th power have made the thing so small that it doesn't really matter. So we have achieved another dimension reduction here. We reduced from our 18,000 dimensional space into this maybe 12 dimensional space. And it should be sufficient, or maybe even it's sufficient to take the first 5, 6, 7, 8, 9 components and say this 9-dimensional space formed by the first 9, as they call diffusion components, is a good space. The reason why we can say it's a good space is because, after all, we've just seen that it's useful to calculate distances between our cells by taking Euclidean distances between the rows of this matrix, and these Euclidean distances, as you can see now, are mainly formed by only the first dozen or so of components. So it could be useful to just work with this. If I want to make if I want to see how this looks like, I can even take the first component and maybe just take the first 2 components and plot that. And say, no, sorry, not the first 2, but the 3rd and 4th. And then I see a bit of a plot. Now this thing, it looks ugly. And when I wanted to show this, I thought, damn it, why does this look ugly? It took me a while to figure out why this looks so ugly. And I remembered that my transition matrix, the eigenvalues, start with 2 ones. Usually you would expect that in a diffusion process you have exactly one eigenvector of eigenvalue 1, namely the final stationary distribution once the Walker has sort of spread out over the walk, and we have reached what the Markov process literature calls the detailed balance, where the probability of the Walker going from vertex I to j is exactly equal to the Walker going backwards, so that any further step doesn't change the probability distribution anymore. And there should only be one such limiting distribution, the final stationary one, unless our neighborhood graph is split into 2 disconnected components. Then you have 2 graphs where you have a diffusion process independent of them, and each of them has its own stationary distribution, and any linear combination of these 2 stationary distributions is, of course, again a stationary distribution, and hence the eigenspace corresponding to this stationary eigenvalue of 1 is 2-dimensional. So this here indicates that our matrix has 2 components. And we can easily see what these 2 components are by checking out the first eigenvector. $vector, or the first 2 eigenvectors. This is one first eigenvector, and you see there's a couple of cells which are on top here and the other are below, so probably greater 0.02. This thing here will show me which let me see if I can show you how this looks like. The UMAP, I plot the UMAP embeddings and make color like 1 plus. See if this works. Yeah. So this stupid thing here is disconnected from all the others. It doesn't have any connections with the rest. And this is why now our eigenmap looks strange. We could try to make a connection, but maybe the easiest is, as we are only interested in the lineage, subset our matrix to only the cells along the lineage, kick out the red one and all the others, and then continue with that. So that's what I've done here. I said I reduce my adjacency matrix to only the cells in the lineage, recalculate the eigenvectors and eigenmatrices, recalculate this 300-dimensional thing, and once I've done all this, let me go down here. Diffusion space in lineage adjacency matrix. Here I've now go down to this last 300. And once I've done that, I should get more or less the same diffusion distances as I had before, because they shouldn't change only because I have removed a component which is not connected anyway. Of course, I've removed a bit more which is connected, so I might have kicked out a few shortcuts, but overall it shouldn't have changed too much. And what I've done here now is I plotted now, this time the eigenvectors. These are the first two eigenvectors, so the first two columns of this matrix U. And each point here is, of course, each point is a cell with the x-axis, its first component in the first eigenvector and this in the second eigenvector. And I colored them in the same way as in this U-map, so the stem cells. So red, the activated green, then the cycling cells cyan, blue, and magenta, the neuroblast brown and green, and the neurons purple. And as you can see, I can see this reconstructed here, this red, green, and so on, just by plotting the two eigenvectors, the first two eigenvectors against each other. I already see my lineage and see the cells in the correct order. I can now really read off, okay, this will be the starting cell, when it goes on, this is the cell cycle, when we are finishing, and here in the eigenvalues. So I can really read off the diffusion time. I can also see potential branchings in this thing, and Kaufman and Lafon call this a diffusion map. And now if we look a bit at our eigenvalues, here's to the 300s component, as you can see, they fall off quickly, but they don't fall off that quickly that it would be okay to only look at the first two values. You can also look at here again the squared plot call sums, this thing. And here I can now see, it seems that I get a reasonable reclamation of my whole thing by taking the first 5 dimensions. I've now plotted for you the first 2 dimensions, but with the first 5, I should get a decent way of recreating the whole thing. And this is now an interesting finding in order to say something about the intrinsic dimensionality of our state space. Because after all, how many numbers do I actually need to describe the state of a cell? At the moment, we always used our PCA space with its 50 dimensions, but we assume that there's a submanifold in this PCA space, and in this submanifold, things might look differently. So let's imagine that this here is the PCA space. 2-dimensional for me now, but these are the 50 dimensions. And this is the submanifold on which the cells actually sit. Because there is random noise, they don't sit exactly on the submanifold, but they scatter around that. But because we use diffusion distances, and you remember the point of the diffusion distances is we chose these 300 steps in order to smooth out small distances. So the diffusion pattern of this cell and that cell will be exactly the same. So that the derivation in this direction I can't see. So after I did this, I used this inherent smoothing in it, I now got this 5-dimensional pattern that I see here. And this 5-dimensional pattern seems to describe everything well enough that if we now were to take back our eigenvector u and multiply this thing by this u, we would get back to a matrix of which we now know that it would be a 5-dimensional submanifold of our 50-dimensional PCA space. So we may conclude that this lineage is actually at most 5-dimensional in our 50-dimensional state space. And this is now the core of what people call the manifold hypothesis, that whenever you have any kind of high-dimensional data set, be it machine learning or be it single cells or whatsoever, it is quite common that they in reality sit on a low-dimensional submanifold and only lift off from this submanifold a little bit by random noise. And this construction that we've now done allows us to see our intrinsic dimensionality. Of course, it's a bit fuzzy because is it 4 dimensions? Is it 6 dimensions? Does this here still count or not? But it's certainly not many. And certainly these dimensions, these 5, 6 numbers are useful to describe the state space. And if we look back at this state, we can already see that obviously maybe this X and Y is not good directions, but this direction here, going along the green line, is clearly the one direction which allows us to understand how this green cell goes along this, how this green cluster evolves. And we could now check in the remaining 5 eigenvectors to see, is this really linear in the whole eigenvector, or is it maybe more sheet? If you look at the light blue, at this blue thing, for example, it seems to be a more 2-dimensional structure. And now we are getting really towards the possibility to understand the intrinsic pattern. And this is in a way a bit the holy grail in all high-dimensional data analysis of machine learning, to understand the intrinsic dimensionality of your submanifold. And in this way, we now got it here, that we can say, yeah. And this is one way of getting there. What I've also then done is that I switched over to the Laplacian eigenmaps, so to the continuous pattern, and did the same here. And I don't really have the time to go through this now in detail because I wanted to show you a couple other things. Maybe we do this next time. But as a look ahead, you can already see what I've done here. I again took this, subset it on the eigenvectors, took my adjacency matrix, and then I calculated from the adjacency matrix, not the transition matrix, but I calculated the Laplacian and took the eigenspectrum of that. And then I used the, and then I plotted here the first and second eigenvector of this Laplacian matrix. It's called here the third and fourth because you might remember in this eigenspectrums, I don't take the ones with the largest eigenvalues, but with the smallest eigenvalues, because I'm sitting in that thing and not in this whole thing. So there's this one minus in here, which means what used to be the eigenvector before. In this picture, we were looking at an eigenvalue of 1 and said that's the stationary one. In that picture, where we don't have this, don't have this 1 minus, because we take this eigenvalue is of course changing from being the eigenvalue with 1 to the eigenvalue of 0. So we have to look this time not for the biggest eigenvalues, but for the smallest. Luckily, this eigenspectrum function that we always use here has a useful little argument where you can tell it, don't get me the largest, but get me the smallest by magnitude. And then I get here the 5 smallest eigenvalues. And you see the smallest of them all has eigenvalue 0. That's the stationary distribution. And then I plot now the eigenvectors corresponding to the second and the third smallest, to these two. And if I look at this plot, again, we see something which is not so unsimilar to that one here. Red, green, blue, brown, orange, and this time the purple one sits here. And this is called a Laplacian eigenmap because it's calculated out of the eigenspectrum of this Laplacian matrix of that one here. And it comes from a slightly different picture, but in the end, it gives us a very similar impression of this thing. And again, we can ask how long till now. It's not so easy to see when the spectrum, when the eigenvalues, how many eigenvalues are significantly non-zero, because we look at the smallest, not the biggest, but overall, this thing works quite nicely. Now, I thought I show you so here we have this, no, this was not the page I wanted to show you. I wanted to show you the other one, dimensionality reduction, dimensional, no, this is another one. Nonlinear dimensionality reduction. That was the one I was looking for. I was looking at this plot, this thing, and thought I'd quickly show you to see how the idea history of how this whole thing evolved. Because we are coming from two directions. We can look at this in two ways. One thing is that we talk about what is the intrinsic dimensionality of a submanifold which is embedded in our big manifold. In another way is simply how can we best depict our data in two dimensions. The latter is maybe what you know from cartography. You might, those of you who know XKCD and know the fundamental rule that there's always a fitting XKCD may know this comic. But independent on that, map projection is the typical thing. You have a surface of the Earth. We know the surface is two-dimensional. If we now try to map, to show a map of the world, we have intrinsic problems even though we already know that the manifold is two-dimensional, simply because it's a closed sphere and we have to tear it open somewhere to bring it onto a flat space. You can imagine if our submanifold is not two-dimensional embedded in 3D, as in the case of the Earth's surface, but 10-dimensional in our 50 PCA space, as it's in the case here, we might come up over many more such tearing problems. But overall, what we want is we want to preserve neighborhoods. We want to make sure that cells which are close to each other are close to also plotted close to each other in the cell points. And it took over the decades, it took quite a bit of effort for people to understand what is possible and what is not possible. The starting point of the whole thing, as very nicely put here, is something I didn't even know it was called Samson's mapping. But of course, there's always somebody who said it the first time. And what Salmon said, I think I knew it under a different name, is, well, what we really want to do is we have objects I and j, which have a certain space, a distance dij in our high-dimensional feature space, and we want to arrange them on the plotting surface such that the distance on our 2D plotting surface on our screen, giving as d star ij, is as close as possible to the real distance. And in order to make sure that this, and then he said, okay, this should be maybe a relative distance. That's why he divided it by this. But overall, the core idea is that you have a stress function or an error function which tells you how much the true distances deviate from the distances that you map, and you somehow want to find an arrangement of the points on the 2D plotting surface to minimize this thing here. They say here so nicely that the minimization can be performed by gradient descent, but in practice it turns out that you immediately run into local minima and your minimization gets stuck at all kinds of places. But this was sort of a starting idea that people started with. Let's try to reconstruct this thing. And as you can see here, this doesn't look at neighborhoods. It tries to, in general, preserve all distances, small and large. And one of the important ideas how people got from this idea, went to multidimensional scaling, went to stochastic neighborhood embedding, and went to UMAP. And I want to sort of take next time to follow a bit this progression. One of the crucial insights was that it's unreasonable to hope that we can get this, that we can minimize something like this, which adds up over all pairs of cells and hence over all the scales. We have to make up our mind and say we only want to preserve neighborhoods, for example. Two cells which are, we want to make sure that cells which are neighboring in feature space also are neighbors in our plotting surface, while hoping that the distance between this red cluster to this green cluster mimics the distance in plotting space, so hoping that the large-scale distances are equal, that turns out to be completely unreasonable because it's simply not possible, simply because there are so many more possibilities for two clusters to have the same distance in n-dimensional space than in two-dimensional space, because in two-dimensional space they have to be sort of on a circle, and in n-dimensional space the possibility of possible arrangement of course grows exponentially in the dimension, because the surface of an n-dimensional sphere is exponentially larger than the surface of a two-dimensional, the circumference of a two-dimensional circle. And this is why there's always way more things which need to have the same distance in n-dimensional space as when you can put here. And so one of the first ideas was this idea of saying we have to understand that we can only preserve neighborhoods. We cannot preserve true overall structure, because simply for this we would need to be able to draw in high dimensional space, and we only have 2 dimensions on our screen. Another issue was, as I said, with these local minima, because if you do a gradient descent, let's stop a moment, because we will need this again next time, and think about what it means to make a gradient descent of this error term. And here, if you look at this, a gradient descent means we look at the gradient of this. And if you now look at this with a physics eye, you notice that this is a force field. What we here see is an energy, a potential which depends only on the distance between points, and hence the gradient has to be something like forces. So whenever you have your 2-dimensional arrangement, where points are arranged in a 2-dimensional point, and I have a sum like this one, which goes over all the pairs of points, when the following will happen. One term in this sum might be this pair of points, I and j. And the distance and the value that it contributes to the sum depends on this distance. This value will be the same if the distance stays the same. So from the point of view of this point I, the value will only change if I move I in the direction towards j or away from j. So we know that the gradient of the term from I and j points in the direction of the connection between I of j. And that makes it a force. That means we can understand this as if I and j were 2 points which are maybe charged particles in which either attract or repel each other, depending on the sign of this thing. If they are too close to each other, they repel, and if they are further in plotting space than in feature space, then they attract each other. And so this is what's happening here. In order to do gradient descent, we go through each pair of cells and check, do they come, are they attractive or are they repulsive? And what then keeps happening is that cells get stuck in each other. That, for example, this cell would ideally be here, but it cannot get here because in feature space, let's say this cell is close to that one. But in the beginning, it's here, and it needs to get to that one. And in order to get there, it has to get past these two. but it isn't close to them, so it always will feel a repulsive force from these two and an attractive force to that one. And even though the actual global minimum of it sitting down here, this here is the local maximum, and we can't get from here to here. And that is why gradient descent usually doesn't work. And a lot of the effort of doing something like t-SNE or UMAP when it comes is essentially of getting around this problem. And that's something I will show you. I think I will come to that next time, how to do that. What I now want to point out is, quickly want to give you a little primer on two more things. One thing is, of course, all this stuff is general. It's not stuff for single cell sequencing, but it's stuff for machine learning that we have since long. And there are some established standard test cases that have been used for decades now to always test these things. And I think I should show you the two most common test cases, and we'll try them out later. The first one is the Swiss roll. The Swiss roll is eine Biskuitrolle in German. This here is called a Swiss roll, this cake here. You bake a biscuit dough, you put cream on top, and then you roll it up. If you want to do this mathematically, you do the following. Where have I put it? You first start off by selecting points from a rectangle. Here I select x coordinates uniformly between 0 and 50, and y coordinates between 0 and 6 pi. Then, and this is my biscuit dough sheet. And then I roll it up along the I roll up the y-axis by turning the y-axis into a radius. And to make my cake a bit fluffy, I add a little bit of noise to it here by adding uniform values between 0 and 1. And now I get a three-dimensional coordinates by saying the x coordinate is what it was before, and the y and z coordinate are now the cosine of y and the sine of y multiplied by this radius here, which is also y. And here is now a plot how this looks like if I look at it head on. So x and so the second and the third dimension. You see, this is my Swiss roll rolling out and out and out, and this is looking at it from the side. So this is what used to be the x coordinate of my sheet, and the y coordinate of my sheet has now turned into the spiral. And from the side you can see here, of course, here it's densest because in projection I'm looking at several layers, and here it's less dense. And now I can take these three-dimensional things. I might do it even a bit more complicated by embedding this three-dimensional Swiss roll by turning it somehow and embedded it in some strangely angled way into, then, say, seven-dimensional space. And then I get this seven-dimensional thing, and then I can ask, can I get back to this? What happens if I subject this to diffusion maps or to Laplacian eigenmaps or to UMAP or to whatsoever, and ask, does this work well or not? It turns out that the Swiss roll, despite its simplicity, is really difficult, and usually you don't get back to the Swiss roll. And that's why it's sort of the standard test case, the stress test to get through all these things. The other thing that people like to use is MNIST. Here, the MNIST database. One of the first important applications of machine learning was digit recognition. Because handwriting recognition, you know, nowadays it works great. You just use your Google phone onto it. But through the whole 70s, 80s, 1990s, this was one of these things where companies and universities always kept telling stories. Handwriting recognition, we are nearly there. Next year you will be able to scan a piece of paper and it will just type it. And it took till the 2000s to people actually get it to work. So in the beginning, in the 70s and 80s, people said, okay, let's not try to recognize text. Let's just try to recognize numbers. The reason why we wanted to do this was twofold, because there was two kinds of paper which contains a small amount of numbers which you need to read millions of these paper slips every day. One is zip codes, postcodes, Postleitzahlen on envelopes. The other is amounts on checks, because nowadays mail has become a bit out of fashion with emails, but in the 1970s and 80s, postal services worldwide delivered billions of letters a year. And originally it worked a way that when they introduced zip codes, Postleitzahlen, which is just 5 number digits, which allow you to quickly route a letter to the right thing. And the original way how we did this is that they had some conveyor belt, and the letter would appear in front of some person with a keypad, and the person would just read off 3, 2, 5, 6, 7, 3, 2, 5, and we had thousands of people whose job was to type hundreds of thousands of letters this way. And the same with all the payment, which was done not by electronic bank transfer, but was done by writing paper checks, which also had all the amounts and so on being read off. So there was a huge demand to automatize that. And this is why this is sort of the first big application of machine learning, build a machine that can automatically read the zip code on the envelope of a postal letter. And hence there has always been this database of a million codes just scanned from actual envelopes written by actual customers of the US Postal Service, which the US Postal Service used to train their attempts to do a machine learning. And it's now the standard data set that you can download. It's called the MNIST data set, and you can download it from lots of places. And each thing is a little grayscale image of 256 by 256 pixels, I think. Or actually, I think it's even, no, 28 by 28 pixels. And here you see how they look like. And you can imagine these 28 by 28 pixels. What's 28 square? Some 3,000 something. You can consider this as a linear vector with 3,000 components, each a value between 0 and 1 for white to black. And the funny thing is, so each of these handwritten digits is now a point in the 3,000 dimensional space spanned by the 3,000 pixels that make up each image. And you can now imagine that all the ones in this space will occupy one region, and all the twos will occupy another region. And you can now start thinking about it. This manifold spanned by all the ones, what dimension does it have? How thick it is? Obviously, it will be, you could parameterize it. Remember, the Americans, they write a one just a slash without the hook that we like to do in German. So all, you might say, where is the one? Is it a bit to the left or to the right, or that in the center? Is it slanted? How far up and down does it go? How thick is the line? But overall, you can probably imagine that over the whole volume of the 60,000 dimensional space, which is not in infinite space, each of the pixel has a value between 0 and 1. So it's the unit interval to the thousandth dimension. And within this thing, this is a well-defined area where you clearly will say this is a 1. And there's another well-defined area where we clearly will say this is a 2, where at least every human would say that. And we want to get there, and we want to see that. And there's probably a lot of spacing between the areas of the 1s and the areas of the 2s. And now the question is, what if I just take this MNIST database, translate it into a 1,000-dimensional thing, and calculate Euclidean distances between any two numbers. For example, I calculate the Euclidean distance between this 3 and that 3 by just subtracting the corresponding pixels, squaring them and adding them up. And then I go into this diffusion map. Do I get all the 1s and 2s and so on in different areas? And actually, that's Laplacian eigenmap MNIST. I'm pretty sure a lot of people have done that. And of course, you find lots of paper where people try exactly this, making such an eigenmap here, for example, and coloring things by what digit it actually was. So that's the kind of way where this all started. Essentially, the Swiss roll and the MNIST database, that's the two example things that everybody, that are always tried first, and whenever you come up with a new idea, the first thing everybody will ask that, does it work on MNIST? Does it work on the Swiss roll? Which brings us to the final topic for today. At least those of you who want to make some kind of test or grade or whatsoever in the end. I mean, this is a bit of a practical course, so there should be a little bit of practical work. So I was thinking about what might be a good homework to occasionally do. And I had a couple of ideas. The first homework that I also talked about with those who were there last Wednesday was simply, let's recap what we've just done. Take our standard single cell data, run on it the code that I've just done and see whether you get the same. But of course, it's easy to cheat there because I've now uploaded the whole code, which brings us to the obvious other thing. Pick one of these things, either the diffusion map or the Laplacian eigenmaps or something else, and pick either the Swiss roll or the MNIST code or another one of these standard things and try to reconstruct, try to run it on this data and produce a plot like this one here. The Laplacian eigenmap of 10,000. Obviously, it's possible because I just Googled it and found this thing, which I would very much assume that it's probably some homework from somebody else, from some other very similar course. Yeah, we can talk a bit more about the details, but maybe I think it would be nice if everybody who actually wants to then get a grade picks something like that. We can talk about what details and tries to get one of them. I've noticed myself it's usually more work than one expects. In principle, it should be easy. The code is there, the data is there, but till you get all this loaded and brought in the right shape, it takes you a couple of hours. So I don't think it's fair to say we do something like this every week, but once or twice it's maybe a useful exercise such that you try out, does this actually work on my computer with my own coding? If you feel inspired now, try the diffusion map or the Laplacian eigenvectors on one of these standard example databases. If this sounds boring, or if you want to do something with actual biological data, let's see what comes to my mind next week. But that was what just came to my idea now. I don't know, does this make any sense to you guys? It's probably just to try out. I'm also still not sure. I hope all of you have enough programming skills that with some trying, even if it's rusty, in case you haven't done this kind of stuff for a while, it's probably worthwhile to try to get your skills back. To be honest, I haven't really thought about this. This dawned on me only yesterday that maybe I should say something like that. Make something nice like that, make it as like a nice notebook, give it to me at some point in the next couple of weeks. Not like tomorrow if it takes, ideally, do it before I, for whatever reason, do the same and upload it, but I think I now won't do this for MNIST or something like that. Okay. Yeah, we're now through with this. As I said, no problem class or exercise on Wednesday. So we'll all meet next week on Monday. And what I had in mind is that I then talk about this neighborhood embeddings and this UMAP. And when we see a bit about why these things, even though they sort of are simple, actually work better than these diffusion eigenmaps. Last question, does anybody happen to already know what the Laplace-Beltrami operator is? Good, that's good, because then if I explain it wrongly, nobody will notice, because my differential geometry is also a bit rusty. See you next week.